Welcome once again to uh, the next video of YouTube channel Tech Guru Gautam Prasad. Here also we are going to discuss series RLC circuit analysis, but a few things that were left we could not cover in the last video will be covered in this video. So R, L, and C resistance, inductor, and capacitors are connected in series and supplied with a AC source. So instantaneous current is Im sine omega t. Im is the peak current, right? So far, we have seen that the basic passive components, resistance, inductance, capacitance, have very different phase relationship with each other, connected to a sinusoidal supply voltage. In the pure ohmic resistor, the voltage waveform are in phase with the current. In a pure inductive circuit, the voltage waveform leads the current by 90 degree, giving the expression of ELI. In a pure capacitive circuit, the voltage waveform lags the current by 90 degree, giving the expression of ICE. And this phase difference phi depends upon the value of the reactive value component being used, and hopefully the reactance X is 0 if the circuit element is resistive, positive if circuit element. This phi will be 0 for the resistive circuit, it will be positive for the inductive circuit, and it will be negative for the capacitive circuit. That is what it wants to tell you. A resistor, resistance, reactance, impedance are 0, and Z will be equal to R. Complete impedance of the circuit in the resistive circuit is equal to R. And the phase difference is 0 is shown like this. For an inductive circuit, purely inductive circuit, total inductance is, reactance is omega L, and Z L equal to J omega L, omega L at an angle of plus 90 degree. And for the capacitive circuit, purely capacitive circuit, it is Xc equal to 1 upon omega C, and Zc, that is total impedance of the circuit, is 1 upon J omega C. So 1 upon omega C at an angle of minus 90 degree. So the voltage lags in the capacitive circuit, voltage leads in the capacitive circuit. Uh, Instead of analysis of each passive element separately, we can combine all these together into a series RLC circuit. The analysis of the series RLC circuit is the same as that of the dual series RL and RC circuits we looked at previously, except this time we need to take into account the magnitude of XL and XC to find the overall circuit reactance. Series RLC circuits are classed as second order circuits. This is important. Series RLC circuits are considered as second order circuits. So this is noteworthy because they contain two energy storage elements, an inductor and a capacitor. Consider RLC circuit below. So the voltage across this resistor is VR, voltage across this inductor is VL, voltage across this capacitor is VC. And instantaneous current is Im sine omega t. The RLC circuit here shown has the single loop with instantaneous current through the loop being the same for the circuit element, since the inductive and the capacitive reactance XL and XC are the function of frequency. The values of XL and XC depend on the frequency. Then the individual voltage drops across each circuit element RLC will be out of phase. If I is equal to I max sin omega t, the instantaneous voltage across the pure resistor is in phase. This is a repetition and this has been shown pictorially here that the voltage VR is in phase with the current, and this voltage in VL leads the current, circuit current. It means the circuit current I that is traveling, the voltage in the inductor leads, the voltage in the capacitor lags. So here, with the help of a vector diagram, it has been shown uh, the VR is in phase with the uh, VR is in phase. It is shown along the x-axis, but it has been VL has been shown vertically upward because VL leads and VC is lagging. That is why it has been shown downward, minus 90 degree, and this is plus 90 degree with respect to VR. So that is what that vector diagram means. And here the relationship of VR and the current, circuit current has been shown. VR and I are in phase. Here VL is advanced by 90 degree. So it is VL is leading with respect to I. But here in the case of the capacitor, VC is lagging with respect to I. Alright, and this means then we cannot simply add VR, VL and VC. So in order to get the total effective current, you will have to vectorially sum them. So there is a Vs as the phasor sum of all these three voltages combined together, you will get the complete voltage, total voltage, Vs, if you vectorially sum them. The Kirchhoff's voltage law, KVL, for both loop and the nodal circuit states that around any closed loop, the sum of the voltages around the loop equals the sum of the EMF. This is the statement of the KVL. KVL states this thing. So that's it. And then applying the rule uh, here, we will find KVL will do this Vs minus VR minus VL minus VC. This sum has to be around the loop. Uh, it will be equal to 0. So Vs minus VR is IR, VL is LDI by dt, and VC is Q by C. So if you uh, change the sides, it becomes Vs becomes equal to IR plus LDI by dt plus Q by C. So the phasor diagram for the series RLC circuit is produced combining together the individual phasors. So here is the diagram. You have a VL here, you have VR along I, and you have VC on the negative side of the y-axis. On the positive side is VL, and the resultant Vs is along this side. Diagonally, it is going in the positive side. So VL minus VC, here we have taken into consideration that VL is greater than VC. So VL minus VC plus VR is the effective voltage, and that is equal to Vs. So this is vector sum of all these. You know, this vector is the resultant of difference of these two, VL minus VC. VC is smaller here and VL is little longer here. So there is a difference. The difference is this VL minus VC, and VR is along the x-axis, VL minus VC along the y-axis, and here it is the difference plus VR, difference of VL and VC and VR. So here this is called voltage triangle. Triangle is giving you the resultant, and you can uh, conclude here that from this diagram that Vs square will be equal to Vr square plus Vl minus Vc to the whole square as per this triangle. So if you consider this triangle, you will get this result, and this will help you in calculation of the total voltage in terms of the voltages given. VL, VC are given, and then you have to calculate Vs. Then you can, this equation is going to help you. VR is also IR sine omega t. IR sine omega t plus 0. That is I into instantaneous value into R. VL is also IXL sine omega t. That is I into JWL. VC equal to IXC sine omega t minus 90 degree, and that is equal to I into 1 upon j omega c. I into xc you can say. Here I into xl you can say. So VR is equal to IR, VL equal to I into XL, VC equal to I into XC. If you are substituting this value in the equation that we had derived here, in this case, if you substitute all these values, you will be getting this IR square, I XL minus XC square. So if you take I square as the common, you can remove the square uh, uh, because of this square root, and this will result into I. So Vs becomes equal to I into a square root of R square plus XL minus XC to the whole square. So R square plus XL minus XC square is equal to Z basically. So Vs becomes equal to I into Z, where Z is nothing but the value of Z in terms of RLs, R, XL and XC. Alright, so this is how this analysis goes on. And then in this series RLC circuit, it can be seen that the opposition of the current flow is made up of three components XL, XC, and R. All these three things are opposing the circuit current. Circuit current is being opposed by these all three. That is capacitive reactance, inductive reactance, and resistance. They together are opposing the circuit current. So XT is defined, total reactance is the difference of XL and XC. It is sometimes XC minus XL, it is sometimes XL minus XC, whichever is greater. And thus the total impedance of the circuit being thought as the voltage source required to drive the current through it. The impedance of the series RLC circuit, Z square equal to R square plus XL minus XC to the whole square. It is like this. XT equal to XL minus X square. This all, it results into uh, when this XL for the frequency for which XL becomes equal to XC, that we have already seen, resonance occurs because the circuit becomes purely resistive here, and because the impedance is minimum, the current goes maximum in this situation, and that's called resonance. So we had also seen the value of cos phi is R by Z, sin phi is XL minus XC upon Z, and tan phi is XL minus XC upon R. So here is example, and we can go through this to better understand this situation and this RLC circuit analysis. Here is it. A series RLC circuit containing resistance of 12 ohm and inductance of 0.15 Henry and the capacitor of 100 microfarad are connected in series across 100 volt 50 hertz supply. Now we have to calculate the total circuit impedance, the circuit current, and power factor, and draw the voltage phasor diagram also. This is the challenge. So here is the circuit. VR, VL, VC is given. The values of R, L, and C is also given. So XL can be calculated directly from the given values. 2 pi FL is the formula. Put the values and you will get XL is 47.13 ohms. Capacitive reactance can also be found by the formula XC equal to 1 upon 2 pi FC, and substitute the values. You will get the value to be 31.83 ohms. And the circuit impedance can also be calculated in the circuit. Z equal to square root of R square plus XL minus XC ka whole square. Z is equal to 12 square plus 47 into 13, 47.13 minus 31.83 to the whole square. If you calculate these values, you will get 19.4 ohm. So total impedance of the circuit is 19.4 ohm. Now, having calculated this total impedance of the circuit, now you can calculate the current in the circuit. So I will be equal to Vs upon Z, and if you substitute the values, you get 5.14 amperes of the current is flowing in the circuit. Now you can calculate the voltage drops in uh, the circuit, the passive elements, like voltage drop in the resistor is I into R, 5.14 into 12. Substituting these values, you get 61.7 volts. VL, I into XL, 5.14 into 47.13, and 242.2 volts is the result. VC is I into XC, 5.14 into 31.8, 163.5 volts. Circuit power factor now can be calculated using formula cos phi equal to R upon Z. So if you substitute the value of R and Z, you will get 0.619. Now if you take the inverse, cos inverse of this figure, you will get 51.8 is the lagging angle. In order to draw the phasor diagram, you have to draw first the VR, then you have to draw the value of VL, 242 volt, and then you have to draw VC, right? And this is nothing but, this length is nothing but VL minus VC. So this is VL minus VC, and that is 78.5 volt. And if you join this origin with this value of the V, then you get Vs. So Vs is nothing but 100 volts. So that is vector sum of VR and V basically. So that's it in this uh, series resonance circuit analysis. And let us summarize it. In the series RLC circuit containing the resistor and inductor capacitor voltage source of Vs is the phasor sum of the VR, VL, and VC that we have seen. And everything that we have already discussed has been repeated here. So I'm not going to repeat it for you. Thank you very much for being with me and enjoying this video. Keep on interacting. Uh, you can interact with me in the form of your comments. Your comments are very valuable to me and tells me how I can improve the video and how I can make this video better for you. Stay with me, stay tuned. Thank you very much.